Our next speaker will be Pelle. Adam joined the Budapest office as the second engineer nearly 2.5 years ago. Since then, he's been driving efforts around machine learning, model integration, and building robust data architectures. Outside of work, Adam is a proud new dad, juggling code and diapers in equal measure. When he finds a rare moment of free time, you'll likely find him deep in a DIY project. Think smart home setups and garden hacks, jamming on his electric guitar, gaming, or diving into a good book. The title of the talk is Machine Learning in Production. Please welcome on stage with a huge round of applause, Adam Pelle.
Hello everyone. It's really nice to see you all here. I'm Adam. I'm a staff engineer at Marshmallow, and today I'm going to talk about machine learning in production. Now it's a bit more focused talk on the operational part of machine learning and not really the depths of the algorithms and training pipelines, because this is focused on of how we keep the lights on, basically, for those endpoints in production. Okay, so before I start, I just wanted to say that last year I also had the pleasure to give a talk here, and I kind of missed the chance to come up with marshmallow jokes, but this time I'm going to change it, so stay tuned and let's get started. Okay, so I split my talk into 3 sections. First, I'm going to talk about a brief history of how we got here that we are at today. And then I'm going to talk about data-related issues or data flows, data pipelines that we pay attention to, and finally how we verify the endpoints in production. Okay, so let's talk about the history. Right, so in the beginning of times, or actually a couple years ago, there were product engineers who wrote services, wrote the code base. And then these services emitted usually offline, usually data to the offline warehouse, Snowflake or any other warehouse. And then on those data scientists usually perform the data intel or data analysis without any live endpoints. So these are offline data analysis. And they really extracted insights from the data, and these insights then fed back into the product pipeline, and then the product engineers acted upon them. Now, what are the problem with this? Is basically it's offline, it's reactive, and it's very slow. So, what changed? So basically, there is a demand came to really do real-time intelligence. If you talk about insurance, then we have use cases which really requires this type of immediate intelligence extractions, like risk scoring, fraud detection, or dynamic pricing. So when we get a quote and we need to return a price for that insurance code, then we need to calculate these things instantly on the fly. Yeah, of course, and also fast iteration is really crucial here, so we need to get to market as soon as possible. So previously, offline models moved into production in an instant, and it was a very, very quick and fast process. So what changed really? We all know that sentence. Let me get back to you in next week. Changed to let me get back to you in 150 milliseconds. So speed is the key here. Okay, let's talk about numbers a bit. So at the moment, Marshmallow has classification and prediction models in claims, fraud, and pricing domains of a business, but we're planning to expand to every major domain inside Marshmallow. We have 14 online inference endpoints, which means that these endpoints are basically let's say microservices that we use for online inference in production, but we have a lot more models and those endpoints, around 25, which means that we have multimodal endpoints as well, and we have a lot more offline models for still doing offline analytics on the data. The busiest endpoint receives around 30 requests per second traffic for P99. It's not a lot, but still it's enough that we need to worry about auto-scaling and resource requirements for those endpoints. And what are the future plans? Well, we would like to have more than 100 models, so it's like we are growing like crazy in this domain. And like I said, we would like to add these models into every major part of the business. So what it means? Well, it means that in 1 year time we probably have more models than actual marshmallows in the Office snack bar. But I'm sure the Office teams will make it a pretty fierce competition. We'll see. Okay, so how we are doing online inference? If you're using AWS SageMaker, if you don't know it, it's basically AWS offering a complete platform to deploy and train machine learning models in production. This is, like I said, this is like API endpoints, similar to any other microservice that we have in the business. We call it using like HTTP REST calls. Okay, so we also have a lot of toolings, just to make bootstrap these endpoints pretty fast. We have a project template written in Python. I didn't mention it, but we use Python as the main language for these endpoints. So we have project templates in Python. We also have helper libraries just to facilitate the common task and common logic in those endpoints. And the deployment happening via CI/CD. So we're basically building Docker images. We have a base image, a base Docker image, and then these endpoints will add the code base onto that image. And we also do canary releases. It's somehow provided by SageMaker by variants, but we also do sometimes customized releases. For monitoring, what I can say, we just monitor the 4 golden signals like latency, throughput, error ratio, and saturation, like we do for any other microservices. Okay, are we done? Not quite. Oh, sorry. Not quite. So let's talk about data flow. So this graph that you see on the screen is basically an oversimplified, very high-level data pipeline of a product. Of course, a lot of components, a lot of moving parts. It's very simplistic, but in theory, that's like a usual setup of a data flow in an IT company. So we have services sending analytical data to a data pipeline, which are usually some sort of streaming solutions like Kafka. And then from this data pipeline, we receive the data into an offline warehouse in a raw format. It's called raw because it's untransformed. It's just the really raw data that we receive from the services. And then usually data scientist team doing some transformation, extraction, some sort of ETL job on those data. And then we get the staging form of the data, which can be used to train those machine learning models and then deploy those models into the endpoints. And then those endpoints could be used by services as live inference in production. Now, without going into graph theory, what you see the circle on that graph. So the data started as analytical data and then ended up as production operational data. So what it means? It means that the operational data equals to analytical data, so there's no distinction between them if we add machine learning models into the picture. So we can't really get by anymore by saying that, oh, it's just analytical data. It can be good if we just do using best effort data emission from services. If it's sent, it's sent. If not, then that's life. It's no longer true because it has consequences. And let's talk about those consequences. Like, first of all, data quality. So here data quality matters more than ever because the machine learning model success are explicitly bound to the data. So it's basically if we send poor quality data into the models, then we could get compounding errors downstream or any such sort of problems. So it's garbage in, garbage out. if we have missing fields or inconsistent mappings, that even a small inconsistency can cause like significant prediction degradation. So these really require some standardization and warrant some consistency for the transformations. And yet another problem came in. So there's a trade-off between a service optimization and the machine learning precision. Because if we want to get a model very accurate, very precise, then we need to feed those models with lots of data. But of course, services usually don't want to deal with that many data, so it's just a need-to-know approach. So if we use the services to feed the machine learning models, then we need to somehow find the middle ground, like how to actually do that to keep optimize the data flow in the services, but still feed the machine learning models with enough data. And it also creates an organizational tension which requires clear governance. But if I have to summarize this, the consequences, I could say that data quality really matters more than ever, because data quality is like a marshmallow in a campfire. We ignore it and suddenly everything is on fire. Okay, let's move on. So how could we empower data quality? Well, we could use a feature store, but before we go there, let's just talk about what is a feature. So a feature is a model input derived from the raw data. It's like an interface between data coming from the services and the model. It's very simple. Basically, there are multiple types of features, let's say. For example, on-demand features, which is a plain simple computed value. If I want to give an example from the insurance world, let's say a risk score. So we receive like a bunch of data about the customer, about the user, and then we calculate a score from those data on the fly. We don't need any other external data for that, only the input data. Another one is dynamic or aggregational data. Again, staying with insurance domain. For example, in order to calculate the price, we would like to know the vehicle values that a particular person tried to insure in the last 5 years. It's a bit, we need to aggregate those data, we need to look up those data per customer. So it's really like a bit of an aggregation needed there. And finally, embedded features, which gets updated periodically. For example, we would like to know about the relation of the vehicle value across the market average to calculate the price. That's also some sort of periodical job needed to continuously update the market average data. Okay, so what are the benefits of feature store? Okay, first of all, what is a feature store then? Well, as the name suggests, it basically stores the features, stores and manage these type of features, even for online and an offline mode as well. So we could use it for online inference and also for training the models. Okay, so benefits, versioning. So it's able to version these features. We see the history. We can change it, and everyone could see. We change the features, and everyone could see. Okay, what happened with those particular feature. It's also consistent. So the teams could reuse the features across models, and it really ensures consistency. So we can avoid the situation when each and every team doing the same thing a little bit differently. And it's also automate ETL jobs. For example, we introduce a feature store today, but we are interested in many features from last year. Then it can also help us to backfill those data without any sort of additional configuration. There are multiple examples for a feature store, a lot of big players out there. For example, Tecton or Feast are good examples. Tecton is a more like a boxed solution, like a all-around. It contains every part of the feature set that we could imagine about feature store. And Feast is an open source solution. You need to maintain it and host it for yourself. At Marshmallow, we use Tecton, by the way. Okay, another type of problem that we need to monitor is basically drift detection. There are many types of drift, and drift means that some aspects of the data change over time, and we need to be aware of multiple types of drift, but I would like to call out two. So first of all, data drift. Now, data drift means that the input distribution changed over time, which is often caused by market conditions. For example, pandemic is a great example. Everyone stays at home, so the vehicle mileage details are kept very low because no one is using the vehicle, and that's like an external change that we need to be aware of. How? Well, monitoring, and we could compare the test data set which was used to validate the trained model, and the production data set distribution. We can compare these two and see whether there's any change. Another is concept drift. It's a bit more supple. So it's basically measuring the relationship between the input and outputs. So a good example, for example, if you'd like to track the claims, vehicle claims cost, and then we see like a repair shop started to increase cost for vehicle repairs, then the previous ground truths that we used to train our model with is no longer true because the repair shop cost increased. So in those situations, it's also very important to monitor this, and we can compare the training data set with the production distribution. Okay, so how could we remediate this? Like very easy, we need to know about this. So like monitoring is really, really important. There are a lot of statistical methods to monitor drift. For example, PSI, which is the population stability index, or even the Kolmogorov-Smirnov test are also good statistical methods to compare distribution of the data sets. Okay, and of course we need to retrain the models just to keep up to date with all these external changes. We could do it reactive and proactive way. So reactive, when we saw something changed, then we do this training. But proactive is usually better when we say that we train the models every week. But that of course requires some automation. Okay, and finally let's talk about the verification of the models. So first of all, why is it important? So in our use case, these models power a lot of parts of the business, like pricing, fraud check, risk scoring, and these parts have direct connection to the revenue and the user experience in our case. So they're very important that these models are working fine. And also, insurance is very well regulated business. So if we do it wrong, then we could get ourselves into trouble in sort of compliance or even make any legal problems. So that's why we introduced production standards into our endpoints in the same way that we do for our microservices. So we measure latency. We have latency SLAs defined, and also these endpoints need to be highly available. And also the code quality and the testing requirements are also very important, just to ensure these SLAs are met. One important aspect I would call out, so I mentioned at the beginning of my talk that we use project templates. And it's actually very challenging. If we introduce changes to that template, then how do we actually propagate those changes into existing models? Now, for trivial changes, we could use a lot of tooling. There are a lot of tools out there which could run a script on a GitHub repositories and create pull requests, so that's pretty easy. But for other changes, when we, for example, add the new test, it's pretty challenging because it's not really trivial thing. You know, you need to mock things differently at each and every model, and for that we started to experiment with AI agents just to iterate over every model and add those tests. Okay. Contract testing. So this is again a very important topic. It's well, I would say it's very old for microservices that we are testing a contract. It's like it's a very old thing, but we started to do that for endpoints, machine learning endpoints as well. So because contract testing can ensure that the endpoints and services communicate reliably, and it prevents integration failures before deployment. It validates the input schema, required optional time constraints, time formats, etc., etc. And it also validates the outputs, so the response structures and the error handling patterns are also very important. In the picture, you see a traditional pack test. I don't want to talk about very deeply of pact. We don't have time for that. But if you don't know it, basically there are two actors in the setup. We have consumers and providers, and the consumers generate expectation against the providers, and the providers verify those expectations against themselves. So that's how the pact works. But we use a bit of a twist. We use a bidirectional pack testing approach, So in that setup, the consumer role is intact, so it doesn't change, still generate expectations. It's like in a traditional packed setup. And we are, of course, we are a Java company, so we use WireMock packed to generate the packed from the consumers. Now, if you don't know, WireMock is a network testing tool. It captures all the network calls, and then it can actually be used to generate the packed files from those network calls. And then on the provider side, we don't actually validate these packs directly, but instead the provider has like a contract schema, which is usually an open API document in a Swagger JSON file. And we use that schema to upload it to a so-called broker, a packed broker. And then the broker doing this check to validate the consumer packed against the provider contract. And the good news is that even before we introduced contract testing, we used the Open API contracts for these endpoints, so it was a no-brainer change for us. And it's very easy to generate these Open API documents. We use Pydantic for the endpoints, so from Pydantic it's super easy to generate the Open API contract. Okay, but one thing which is important here, so the provider does not verify its own schema. So what it means, so let's say that we are working on something in the endpoint, and then we suddenly made a previously optional field required because we introduced some logic that requires some fields, and we forgot to update the schema. Then basically it was all for nothing because we have a contract, but it's not valid for the endpoint. So what could we do in that case? We could verify the schema. Again, there are tools out there to do these integration type of tests to verify a contract. For example, schema thesis or Dread. And these tools work in a way that it generates a random data based on the contract, and they actually call the endpoints. And you observe the behavior of the endpoint, so whether anything fails or succeeds, etc., etc. So it's all sounds easy, but it's not really that easy if we, dig a bit deeper into generation, how we generate this data. We are an insurance company, so we deal with a lot of financial information, so we use decimal types for those type of fields. And then we decided to represent every decimal type as a string, just to avoid, serialization, rounding issues, etc., between different languages. But if we use strings, then we couldn't really define minimum, maximum boundaries for those fields. So we introduced custom fields for those type of things, and then we had to build support for those custom fields across the stack, which is very cumbersome. It was hard. But overall, I would say it's definitely worth it because, in my experience, schema verification catches more bugs than we do next to a campfire, and it's really true. So, in my experience, that's like a biggest root cause of issues with endpoints. They deal with a lot of data. It's so easy to forget stuff, and then we get into trouble. So that we had a couple issues with this, and after we introduced schema verification, then things definitely improved. Okay, and finally, I would like to mention backtesting. So backtesting is a dedicated testing strategy where we use historical inputs to replay those inputs for the models, and we see the changes. So let's say that we would like to introduce a pricing change, and then we expect that we could give like 20% lower prices. So what we do is we prepare that change, we create a pull request, and from that branch we build a Docker image, and then we basically simulate those changes from the previously production data. If we need that, we anonymize the data. And then we check what happens, whether it's really what we expected or it's something different. One important thing that if we do this, then the old data needs to run through again with the production state, because most likely when we calculated an old data, then we did that calculation with a very old model state. So we need to redo that calculation with the up-to-date model state in production. Okay. And we could use that to, various things like comparing prediction, detect regression, or even statistical evaluation. And yeah, it's really important for us because it's about building confidence. So when we release something that we know that okay, it really does what it's supposed to do, and then we could also mitigate any financial or even legal risk when we make these changes. Okay, so future directions. We would like to introduce better data management. Since we're using feature store, we get some sort of data lineage, but it's not across every product. So what we really want to see is every particular data from the services, how to get from the services to our offline data store, offline warehouse, via feature store. So like across the board, we would like to see the lineage. We couldn't do that today. Data lake access for machine learning. So we'd like to enable our data scientists to self-serve themselves autonomously, and again, just we would like to help them about data discovery, so they could see what raw data available from the services. Yeah, again, we would like to ensure model accuracy. I mentioned that. Scheduled training could really help avoiding drift, and we would like to introduce those type of weekly schedules or even daily schedule model training for every hour models, but it takes time and other additional considerations. And cost optimization, because actually these things cost a lot. So if you start using these things like SageMaker, Feature Store, etc., these really cost a lot. So we need to see what are the possible cost optimizations there, and we would like to build upon that. And that's all I wanted to say today. Thank you very much. So if you're interested about this topic or want to catch up with about everything else, we are here at the booth. So feel free to drop by and have a nice chat. And now, if you have any sort of questions, then I'm happy to answer. Thank you.
Thank you very much. You can see the QR code here. It leads to Slido, so ask away your questions so that we can continue the discussion a little longer. We already have our first one. So what is the biggest challenge for your team from all that you presented?
Yeah, interesting, because basically everything was pretty challenging that I just mentioned, but probably the biggest challenge is timing, because I mentioned it my beginning of my talk, but all these things happened very, very fast because there was a business need to do live inference instead of offline analysis. And first we started to add these models into production without any sort of considerations, just to really get to the market very fast. And then it introduced problems, failures, etc., etc. So we had to come up with a roadmap pretty quickly. So we worked together with MLOps team. Actually, we put together an MLOps team, and then we started to really work on these improvements. So yeah, the timing was the biggest challenge for us.
All right. Any more questions, either online or in person? We're just going to wait a little to see whether new questions roll in. Last chance. All right, 3, 2, 1. Well, in this case, thank you very much for the presentation. Thank you. Round of applause, please, for our presenter. Thank you very much.